Rocks at the bottom of the ocean are making oxygen, and NASA is one of the reasons we know it. Not plants, not algae, not any living thing at all. Deep beneath the Pacific Ocean, around 13,000 feet below the surface, lumps of mineral called polymetallic nodules appear to be involved in splitting water molecules and releasing oxygen in complete darkness. There is no sunlight reaching that environment, and yet oxygen was detected where scientists expected it to be consumed. The discovery challenges. One of the assumptions we have carried about oxygen production and raises a much bigger question. If rocks can create oxygen without biology or sunlight, what else might be possible on other worlds? But this is only one part of a much larger story. The deep ocean has become something far more important than a place where scientists study strange creatures and geological processes. It is becoming a testing ground for technologies that could eventually explore alien oceans. NASA and its partners have been developing autonomous underwater systems capable of navigating without GPS, collecting environmental information, building maps, and operating under crushing pressure. In other words, some of the technology being prepared for future space exploration is being tested right here on Earth, in an environment that is dark, isolated, and hostile enough to resemble conditions scientists expect beneath the ice of distant moons. The story begins with a spectacular failure. In 2014, the deep-sea vehicle Nereus was exploring near New Zealand's Kermadec Trench. The machine had already contributed to more than a dozen scientific publications from only 4 dives. But during one mission, it lost contact with its mothership and disappeared. The vehicle had cost around $14 million, and the ocean swallowed it in a single moment. The loss demonstrated just how difficult and expensive exploration of the deepest parts of Earth's oceans could be. The deepest Hadal environments, those beyond roughly 6,000 meters, remained largely inaccessible to long-term scientific exploration, creating the need for a completely different approach. Part 2, Orpheus and the CubeSat philosophy. Biologist Timothy Shank decided that the solution might not be to build one enormous expensive machine and hope it survives. Instead, he developed the idea behind the Hadal Exploration Program, or HEX, build many smaller, cheaper autonomous vehicles. The philosophy was borrowed from the space industry's CubeSat approach. Rather than putting an entire mission at risk with a single billion-dollar spacecraft, multiple smaller systems can work together. If one is lost, the others can continue collecting data. To turn that philosophy into reality for the deepest ocean, Shank and his team worked with NASA engineers and developed Orpheus, an autonomous underwater vehicle designed specifically for extreme environments. Orpheus weighs roughly 550 pounds, is approximately the size of a Harley-Davidson motorcycle, and costs less than $2,000 to build. That is dramatically different from the $14 million Nereus vehicle that was lost. 2 vehicles were built in 2018 and named Orpheus and Eurydice, after the mythological pair associated with the underworld. Even the material keeping the vehicles buoyant has an interesting history. Their syntactic foam made from microscopic glass spheres embedded in epoxy resin came from spare material originally produced for James Cameron's deep-sea submersible. The same basic flotation material helped Cameron reach Challenger Deep in 2012, and now similar technology helps autonomous robots travel through Earth's deepest trenches. The most important technology inside Orpheus, however, isn't its flotation material. It is the navigation system. Thousands of meters below the surface, GPS signals cannot penetrate the ocean. Traditional deep-sea vehicles often depend on expensive acoustic positioning systems, ships and transponders. Orpheus uses visual inertial odometry, or XVIO, developed by NASA's Jet Propulsion Laboratory cameras, watch the seafloor and identify features such as rocks, shells, coral fragments, and sediment patterns. As the vehicle moves, software tracks those features and calculates the vehicle's position and movement. Combined with sensors measuring acceleration and orientation, Orpheus can build an understanding of where it is without receiving an external signal. The same fundamental approach is connected to navigation technology used by NASA's Mars 2020 Perseverance rover Part 3, a submarine designed for alien oceans. Orpheus doesn't simply navigate it. Remembers maps created during a dive can be stored and used when the vehicle returns to the same area. The machine can recognize familiar arrangements of rocks and other seafloor features and use them as reference points for future exploration. Multiple Orpheus vehicles can potentially share information, allowing one vehicle to discover something interesting and other vehicles to use that information to investigate further. The vehicles also carry sensors capable of detecting chemical signatures associated with hydrothermal vents and cold seeps. Environmental DNA technology can collect genetic material from organisms in the surrounding water or sediment without requiring scientists to physically capture those organisms. Orpheus was first tested in 2018, and in May 2021, it took part in a 2-week expedition aboard the NOAA ship Okeanos Explorer. During that expedition, it completed 8 dives and traveled more than 24 kilometers across the seafloor. It built 3-dimensional maps and detected chemical variations in the water column while operating autonomously in total darkness and under pressures that would be immediately dangerous to an unprotected human. These achievements explain why NASA's interest in underwater robotics goes far beyond Earth's oceans. The real destination is potentially an ocean hidden beneath another world. That world is Europa, one of Jupiter's moons. Europa is covered by an ice shell roughly 12 kilometers thick, and scientists believe a global liquid water ocean exists beneath it. Conditions at the bottom of that hidden ocean could resemble some of Earth's deepest environments. There would be extreme pressure darkness and no possibility of relying on ordinary GPS or direct human control. A spacecraft could not simply send a joystick command through kilometers of ice and hundreds of millions of miles of space and expect an underwater robot to respond instantly. A future Europa, Explorer would need to make decisions autonomously where to travel, what to investigate, what to sample, and when to return. That is why the deep ocean on Earth has become such an important analog environment for NASA. Saturn's moon, Enceladus, offers another possibility. The moon actively releases material from its subsurface ocean through cracks near its south pole. Scientists have detected water vapor, ice particles, organic molecules, and molecular hydrogen in those plumes. Molecular hydrogen is especially interesting because it can be produced when liquid water interacts with rock in hydrothermal systems. On Earth, hydrothermal vents support entire ecosystems without sunlight. If similar environments exist beneath the ice of Enceladus, they could provide conditions relevant to the search for life beyond Earth Part 4, life that doesn't need sunlight. In 1977, scientists made a discovery near the Galapagos Islands that completely changed our understanding of life. A deep-sea vehicle was investigating a thermal anomaly when researchers found thriving ecosystems around cracks in the seafloor. Tube worms, clams, mussels, shrimp crabs, and fish were living in complete darkness near hydrothermal vents where superheated mineral-rich water escaped from Earth's interior. There was no sunlight, yet the ecosystem was rich and complex. The discovery showed that life did not necessarily need sunlight to build a functioning food web. The organisms around these vents were supported by chemosynthesis. Microorganisms convert chemical compounds, such as hydrogen sulfide, into organic material, creating the foundation of a food chain that does not depend on photosynthesis. Before this discovery, scientists generally understood sunlight to be the ultimate energy source behind Earth's ecosystems. Hydrothermal vents shattered that assumption. The energy source could instead be geology. If life can survive in darkness using chemistry and geological energy on Earth, then environments containing liquid water, rock heat, and the right chemistry elsewhere in the universe become much more interesting places to investigate. NASA scientists later studied the Pickard vent field in the Caribbean Sea, one of the deepest known hydrothermal vent systems more than 16,000 feet beneath the surface. There they encountered blind shrimp known as Rhymicaris hybaceae. Vent fluids can reach temperatures around 750 degrees. Yet these shrimp live in dense clusters on rock chimneys. They cannot see, but heat-sensing structures help them position themselves close to the boundary between deadly heat and survivable conditions. Bacteria living in and around their bodies use the chemicals from the vents, while the shrimp depend on those microbes. When the shrimp cluster tightly, they feed on bacteria when they spread out. Researchers